Good morning, or good afternoon. Thursday, October 29. Here's our class session and our mission for today, rational equations and applications. So it's got a very positive thing. It's a little bit like last class session on Tuesday. Very straightforward and procedural. We can just work on the problems straight out of the book. Let's just shoot out some problems and you'll see exactly what you're supposed to do. It doesn't require much of a fancy explanation. Now the applications problems that we're going to give you, and I'll show you where we are on our website. There's two sections we're looking at. Oops, wrong semester, C. On course 119 week 9. We're looking at these last two sections this week, 6.5 and 6.6. So the problems in 6.6, there's some fun application problems. Each one of them, again, is different. Every time someone gives you an application problem, each one of them has to be approached uniquely. But they can be illustrated very nicely with the examples that he has in the book. Okay, so let's dive into it. I sent out an email last night, so just to remind you, in case you did not see that, exam 1 is returned. With most recent homework scores and most recent grade report. So maybe you've already looked at that. You can check that out yourself. And I said in the email last night or sometime maybe early this morning, say, make sure I add up the points correctly. Make sure I did that correctly. Make sure in your grade report that I've got all your homework scores, test scores, and stuff like that. But now you've done one of everything. You've done written homework, XYZ homework, and now an exam. You have one more exam. So you see the whole picture on your grade report. Although right now we've done about exactly 1/2 of the class point-wise. So you're just about halfway there in your grade point-wise. So examine that. Look at the answers I posted to the test and see how you could do the problems if you got more or less points on a given problem. And I also said in the email that if you want to ask a question about how I graded anything, that's absolutely fine. I mean, that's only fair. Make sure you look at the answers before you ask the questions, just so you know exactly what you should or could have done. But then if your answer, if your question is, why did you give me 10 points instead of 12 or 14 points instead of 18 points, whatever your question is, what did I exactly do wrong here? Then whatever your question is, I'll be happy to answer that one-on-one, email or one-on-one meeting. I don't want to discuss anybody's tests here in the class session. Okay, let's look at some rational equations. And the easiest way to look at that is by taking some problems out of the book. Why don't we start with number 1? There's another thing I wanted to do today, and I don't know, maybe experiment after the break. I always have my whiteboard in here so I could write on the whiteboard if I want to. I mean, maybe once I've popped in front of the camera. Maybe I'd like to write some problems on the whiteboard in the second half of the class just to see how that records. and just to see whether that would be a good way of presenting things too. I think writing on the paper is pretty good because it doesn't suck up bandwidth. But I just want to see if writing on the whiteboard, if that's too much video for the system. Okay. Solve this equation. And a curious warning. Be sure to check for any fancy word, extraneous solutions. And this is the instructions for just about every problem in this section. So let's just consider this to be our blanket instructions today. And problem number 1 is x over 5 plus 4 equals 5 over 3. Now, why should I call this a rational equation? Well, remember, a rational expression is just a ratio of polynomials, a fraction made out of polynomials. So a rational equation is just an equation that contains rational expressions. This first problem is not fancy rational expressions. There's just very simple rational expressions, just no squares, no big polynomials, just fractions made out of numbers, 1x in it. So I could solve this problem just by dealing with the fractions as they are, and that wouldn't be so bad. But really, the fastest technique in any problem like this, whether it's problem 1 or problem 50 later, is to eliminate the fractions as soon as possible. And the idea is here, I don't know what the answer will turn out to be. Maybe the answer will turn out to be a fraction, I'll be stuck with it. But I just don't naturally like thinking in fractions. Am I supposed to make common denominators here and make 15? Sure, 15 would be a great least common denominator, but I don't want to think in fractions. Now, as it happens, the technique for eliminating fractions is to multiply by the least common denominator. So I still need that skill that we worked on Tuesday, how to build a least common denominator. In this problem, the least common denominator is 15. It's just literally 3 times 5. So I will physically multiply everybody by 15. That's the x plus 5, x over 5 plus 4 and the 5 over 3. Now I'm not multiplying by 15 to create larger or more fractions. I'm multiplying by 15 literally to eliminate fractions. And this multiplying by 15 instantly eliminates these fractions. 15 times x over 5, 15 over 5 is 3 over 1. That immediately cancels the 5 in the denominator. 15 times 4, well, there wasn't a fraction involved in that, so that's just straight away 60. 15 times 4. On this side, I'm writing every step very carefully right here. In this side, 15 divided by 3 is 5. 15 over 3 is 5 to 1, so this is just 5 times 5. I'm just writing these out before I multiply them out. I could have simply said 3 times x plus 60 is 25. I could have said that right away, but I wanted you to see me canceling as I multiplied. Okay, so now I just solve this for x as I would ordinarily from early first week of class maybe. Subtract 60 from both sides. 3x is minus 35. X is minus 35 over 3. So we have solved the equation, but what about this curious warning right here? Check for extraneous solutions. Extraneous, I guess in plain English, means extra solutions, but actually sometimes when you do these problems, you produce solutions, quote unquote, solutions that don't actually work. And that's what he's referring to there. So why would this answer not work? That doesn't seem logical unless I made an error, and I don't think I made any errors. Why would the solution not work? Well, rather than worry about that, why don't we just physically check it and see if it works? We're checking for extraneous solution. We're checking to make sure if we actually have the answer. So minus 35 over 3 divided by 5 plus 4, is that the same as 5 over 3? Now remember, think about negative 35 over 3 divided by 5. How do you divide? You invert and multiply. So that's 35 over 3 times 1/5. Plus 4, is that really 5 over 3? 35 over 5 simplifies nicely to minus 7 over 3. 4, if I want to make thirds out of it, is 12 over 3. And I've just checked that it actually equals 5 over 3. Negative 7 over 3 plus 12 over 3 is 5 over 3. Yes, this works. Yes, this is a legitimate solution. But then the question is, I never expected it to be anything but a legitimate solution. How could it possibly have not been a legitimate solution? And the answer is not in this problem. This problem is a problem that had no danger in it. Now, by danger, when I talk about fractions, I mean danger means dividing by 0. When we have a full rational expression, it's possible that we have variables on the bottom too, right? So I'm thinking, what if I had some x's on the bottom here and my answer caused one of the denominators to be 0? That's what I'm afraid of. That's what he's afraid of. Extraneous solution would be a number that looks like it works, but it ruins one of the fractions by turning the denominator into 0. Here, none of the denominators could have ever been 0. You say, well, there's only 2 denominators. I guess there's 3 technically if you say 4 over 1. None of those denominators, 5, 1, or 3, could possibly be 0. So there was no danger. So actually, I was pretty confident this was going to work. And we checked it, and it worked. But I could show you another problem where it doesn't come out so nicely. Let's work our way up. That's problem number 1. Let's try number 13. Okay, so we're in 6.5. We're looking at number 13. And it goes like this. 1 minus 1 over x equals 12 over x squared. Sorry, let me adjust my paper. Same 2 instructions as before. Solve and check. But I don't want to rewrite these long instructions here. So solve the equation. Be sure to check for any extraneous solutions. Just let me abbreviate that right now and say solve and check. Before I get going, though, I say check for what? I mean, what am I afraid of in this equation? Not afraid of. What would be wrong? What could be wrong in this equation? When I look at this equation, got an x in the denominator. If x is equal to 0, I cannot use that. What if I do the work and one of my answers is x equals 0? I'll have to throw it out because it's not legitimate. So maybe I'll make this note right at the beginning. I cannot allow x to be equal to 0. Okay, let's go about solving it. Least common denominator. Denominator 1, denominator x squared. The least common denominator in this problem is x squared. Let's multiply both sides by x squared. And I did this in another color just again to focus on the multiplying. Remember, on this side, I'm going to distribute, and I got to respect that minus sign. On this side, I only have to multiply once. On the right-hand side, it's just x squared and divided by x squared. They literally cancel each other out. I get 12 right away. On the right-hand side, I get x squared times 1. I want you to see me writing it. And I get x squared times 1 over x. X squared times 1, sure, it's just x squared. I could wrote that right away. Even x squared divided by x just cancels one of the x's. I'll be minus x times 1. So this is why we multiply by the least common denominator. Some people say it like this: to clear the fractions. To clear out the fractions, to get rid of the fractions. Okay, now I got this problem that looks like a potential factoring problem that we've done recently. How do we do this? Set the whole equation equal to 0. See if I can factor. And then see what the possibilities are. This factors into x plus 4 and, sorry, x minus 4 and x plus 3. So if I multiply these two things together and get 0, one of them has to be 0. And I will write, excuse me, just checking that, either x minus 4 is 0 or x minus 3 is 0, x plus 3 is 0. So this means either x is 4 or x is minus 3. Now, what about the check? Well, I've got something going for me very strong right now, and that is neither one of these numbers is 0. So I'm not going to screw up the denominator. I cannot allow x to be 0. That was what I said at the very beginning. And the two answers I got here, neither one's 0, so that's okay. You could still ask yourself, do they work? They may work or they may not work. But if as long as I didn't screw up the denominator and I did all my work here correctly, they're going to work. Remember to check, though. Don't check along the way. You have to check in the original equation. So if I say, let's put in 4. X is 4. Then is x equal to 4? 1 minus 1/4, the same as 12 over 16. 12 over 16 is cancel a 4, 3/4. 1 minus 1/4 is 3/4. The answer is yes. Let's try -3. Watch your signs. 1 minus 1 over -3. Is that the same as 12 over +9? When you square -3, you get +9. You put the -3 in there, you got to respect that negative sign. 12 over 9, if you cancel 3, is 4/3. And this actually says 1 plus 1/3. 1 plus 1/3 is 4/3. 1 1/3. The answer is yes. So what are my solutions? X equals 4. X equals -3. Both of these numbers worked. Now, I'll tell you that I don't always plug in these numbers here, although if I had time, I should always do it just to make sure I'm okay. But here's the real story. This checking thing is really checking to see if you screw up the denominator. As long as you don't divide by 0 and you did everything else right, of course, sometimes I make mistakes along the way, but as long as you've done this work right, and these answers don't cause you to divide by 0, then they're both going to work. Let's try another one. Today is red and green day on the paper. Maybe I'm thinking ahead to Christmas. Let's look at number 17. Again, there's the two simple directions, solve and check. Number 17 says x plus 2 over x plus 1 is equal to 1 over x plus 1 plus 2. I need to get my reading glasses here to help me out a little bit. Okay, solve and check. But here's a really good tip for all these problems when you have fractions made out of polynomials. Before you start, write down for this checking part what you're afraid of. And I don't mean afraid, I mean what you are worried about. Worry is the wrong word. What you can't allow in this denominators here. If x is -1, you're in trouble. If x is -1, you'll be divided by 0. That's not allowed. So here's what I want to do. Just make a note. I cannot allow x equals -1. If I say that at the beginning, then I won't forget it. If I don't say it at the beginning, I'll forget to check. Okay, now let's proceed. The least common denominator. Again, pretty simple denominators here. Two denominators, they're both the same. You could call denominator 1 on this, 2 over 1, but the least common denominator is just x plus 1 times 1. So now I multiply both sides by x plus 1. With all the nice parentheses so that I keep track of everything. And let's look at the result. Canceling happens here too. In fact, that's why you multiply by the least common denominator, because you always get to cancel things. On the left side, there's only one piece to multiply. X plus 1 cancels exactly, and all you're left with is x plus 2. On the right side, x plus 1 divided by x plus 1, it cancels perfectly, nothing left over, and you're left with a 1. That's the first time you multiply, but you got to remember you got to multiply 2 times with a plus sign in between them, 2 times x plus 1. x plus 1 times 2. You could say it either way. Now, you're cruising along because this looks like a pretty ordinary problem. X plus 2 equals 1 plus 2x plus 2. I'm getting a little bit low, so I'm going to take it over here. X plus 2 equals 2x plus 3. I'm just carefully writing out all the steps. Let's bring the x's to the right side. Subtract x from both sides means x on the right. Subtract 3 from both sides means minus 1 on the left. There's my answer. But what about the check? Well, the moment I wrote down that answer, I got upset or nervous, suspicious. In other words, I do this work and my answer says x equals minus 1. But from the very beginning, I knew that that was the one thing I couldn't allow. So there's not even reason to check this. I mean, let's put minus 1 in here. I get 1 over 0 equals 1 over 0 plus 2. There is no 1 over 0. 1 over 0 is not defined. So this solution that I wish for, it doesn't work. Now, what do you do when you did everything right and it doesn't work? Doesn't necessarily mean you made a mistake as long as my work was correct. But if you did everything right and your proposed answer doesn't work, that just means this problem has no solution. So this can happen when you have rational expressions like this. It's okay to say that the problem has no solution. Think about it this way. You only had one shot and it wasn't legal. You only had one shot and you can't use it. Well, that means you're out of bullets. You got nothing left. There is no answer. This happens, I don't say every day and stuff. I mean, but it just happens once in a while. Make sure you check your denominators. Okay, those are still warm-up problems. Let's try something busier. And he's got other problems in the book. And I'm just looking. And then he's got some word problems going on there. And we might try one of them. But let's still work our way through. I'm just looking at the first page of problems in this section, just picking out ones that are a little harder each time. So let's look at 33. Again, I'll stick to my same instructions. Solve and check. I mean, it's a good idea to check all answers all the time. 33. I don't like 33 very much. Let's change it to 31. It's more interesting. We can come back and do 33 or likewise later. Okay, so anyway, 31. We're on 31. 3 over y minus 4 minus 2 over y plus 1 equals 5 over y squared minus 3y minus 4. So get into this habit with this. This is a rational equation. It's an equation made out of rational expressions, an equation made out of fractions of polynomials. Here, there are no polynomials at the top, sure, but it's still fractions made out of polynomials. So get in the habit, every time you start one of these problems, is that you make a list of the things you can't use. I cannot use 4 I'll just abbreviate and say y is not equal to 4. Can't do that. I cannot use -1. That would ruin that second denominator. Can't use it. So, I should check, is there anything that would screw up this denominator? And I jumped ahead too fast because actually if you factor that, you get y minus 4 times y plus 1. So yes, there are numbers that would screw up this denominator. I've already written them down. Y equals 4, y equals -1. I've already checked those out. I will reject those. Still, it's not bad to factor whenever you can. Okay, so let's go forward. We want to multiply by the LCD. Now, this is the first problem today where the LCD was not just in front of you, just plain in your face. So let's look at this. Remember how we talked about it last time. This fraction lacks a y plus 1 to be equal to that fraction. This fraction lacks a y minus 4. The least common denominator in this problem is y minus 4 times y plus 1. Now, Tuesday, we used that to add things together. Today, we're using the least common denominator in a different way. We're using it to kill fractions. We're going to multiply both sides by that least common denominator to get rid of all the fractions. Now, it's got more pieces here. This problem is bigger, right? But I'm going to do it the same way. I'm going to distribute, multiplying carefully one step at a time, and cancel what I'm allowed to cancel, and respect all the signs that are present. On the right side, I only have to multiply once. So that's nice. And the right side, I got both of these pieces to cancel. So the only thing left is 5. After I cancel these, just left with a 5. Here, don't cross things out as you go because you got to do 2 jobs. But think about it like this. The first time I multiply, I'm going to kill the y minus 4s. They're gone. And I'm left with 3y plus 1. 3 times y plus 1. Don't forget the parentheses. Second time I multiply, I'm going to kill the y plus 1s. And I'm left with 2 times y minus 4. Don't forget the parentheses. And now don't forget the minus sign. I can't ignore that minus sign. Don't rush to multiply this out because you want to make sure that you kept track of the signs. But now that I've done this, I'm happy that, let me get someone else in here. Now that I've done this, I'm happy because I got a problem with no fractions in it. Let's multiply it out. 3 times y plus 3. Minus 2 times y. And minus 2 times minus 4 is plus 8. Now, this equation is more up our alley, just straight ahead. 3y minus 2y is y. 3 and 8 plus 3 plus 8 is plus 11. And that's going to be 5. So now I know what y is. Subtract 11 minus 6. Now remember, this is still only a possible solution. I have to go back and do the check. And what was the check? The check was don't use 4, don't use minus 1. That would ruin the denominators. So now I check this out. This looks like it's okay. I don't think there's going to be a problem It won't ruin the denominators. You might ask, will it actually work? Well, we're going to have to check that. But the thing that you're number one afraid of is dividing by 0. So this is not going to do this dividing by 0. Let's put minus 6 into here. I get 3 over minus 10. I'm just quickly inserting it. Don't forget this minus sign. Now put 2 over minus 6 in here. 2 over negative 6 plus 1. 2 over negative 5. Lots of minus signs. Let's put minus 6 in here. That looks a little annoying. Say 36 plus 18 minus 4. You know, you got to plug in the minus 6 and watch the signs. But you could also plug in the minus 6 here. This is negative 10. This is negative 5. What's negative 10 times negative 5? Positive 50. Now let's get rid of these signs that I don't need. Minus negative 2/5 is just plus 2/5. Does that turn out to be 5 over 50? I'm going to get common denominators. Say 20 over 50 is 2 over 5. Now turn 10, 3/10 into 50, say minus 15 over 50. So minus 15 over 50 plus 20 over 50 is 50 over 50. This answer works. Now, you'll get in the habit after a while of knowing that as long as you didn't ruin the denominators, make one of the denominators equal to 0. As long as the denominator is not 0 with this number, it's going to work if you didn't make anything else wrong. Still, it's no harm in checking it. You should check it. So the solution to this problem is y equals minus 6. Okay, I'll call that a medium problem. It's not the fanciest one in the section. I think we should do a word problem. I think we should try another problem here besides that one. But this I call medium problem. There's a fair amount of writing. And these problems do have some extra writing in them, just like last session, just like on Tuesday. Let's try. I want to try another one. I'm looking. I'm going to try medium hard. So let's look at 41 or 42. I also like 37. 37 looks small, but it's kind of deceptive. I think you should do both 37 and 41, and then a word problem. But which one do I like more? Let's do 37. 37 because it looks smaller. So sometimes the problems that look smaller are the deceptive ones, or the harder ones. So let's say 6/5, 37. So this is the positive part about today, about these equations, is you can learn them just as you go along doing them. You can do that with everything, that's true, but sometimes you need more explanation than others. This is problem 37. The instructions, again, are essentially solve and check. And I want to know what I should worry about. Now, nothing is plainly factored for me. So I think I'll start by factoring. This denominator is y times y minus 1. If I factor out a common factor of y, I get y times y minus 1. This denominator, deceptively small, is a perfect square minus a perfect square. That's a minus b A plus B. Y minus 1, y plus 1. 6 is on top. So look at my denominators. I got a y minus 1, and then a y plus 1. I've got 3 different pieces. This first denominator lacks the y plus 1. This second denominator lacks a y. So that's going to be my least common denominator. All 3 of those pieces. And now I also know what I should check for, or what I should be nervous about, afraid of, whatever word you like to use. What values of y would cause me to divide by 0? If y was 0, I'd be in trouble. If y was 1, I'd be in trouble. If y is minus 1, even just once, nothing wrong with minus 1 in this part, but minus 1 would ruin this fraction. So I have to say y cannot be 0, y cannot be 1, y cannot be minus 1. Okay, now that I've prepared that so I won't miss it, let's multiply both sides by the least common denominator. So this problem's got some extra pieces in it. So let's be careful. Y minus 1, y plus 1. I wrote x minus 1 there for a second. Looks like I ran out of space here on the right. But remember, the right side only had a 0 on it. So I was looking at that. What is these 2 people in here? Y plus 2 over y minus 1. Y minus 1 times y plus 1. On the right-hand side, you multiply all these people times 0. That's not a complicated thing. 0 times these guys is 0. On the left-hand side, though, I do actually have 2 things to multiply, and I have canceling both times. In fact, if I didn't have canceling, I'd be nervous. The LCD was made to cancel these, right? So the first time I multiply, I will cancel the y and y minus 1, and I'll just be left with y plus 1 times y plus 2. There's something I'm going to have to multiply out there, I think. Next time, I cancel the y minus 1, y plus 1. I can't do that with my finger because my fingers are too thick. How about like that? I cancel the y minus 1, y plus 1 with my thumb and over here. And I'm left with a y times a 6. 6y. Except I have to subtract 6 times y. Whatever's up here, I'm going to be subtracting it. 6y. Now, it still looks like I'm not nearly done, but at least I have no fractions. So let's multiply this out. Y squared plus 1y plus 2y's plus 3y's plus 1 plus 2 multiplied is plus 2, subtract 6y equals 0. Just one step at a time. Have you ever... I'm going to tell a joke and do math at the same time. That's impossible. First of all, let's do 3y minus 6y. Is negative 3y. Then I got this 2. Okay, so these 2 belong together. Equals 0. What I was saying, just do this one piece at a time. Are you heard of the Johnny Cash song, One Piece at a Time? Have you heard of Johnny Cash? Somebody Somebody help me out. Just please say you know who Johnny Cash is. If not, go Spotify him.
Ring of Fire.
Ring of Fire. Good, good. So there's a typical one right there, and Folsom Prison Blues. But go look up Johnny Cash, one piece at a time. Kind of a fun song. Okay, now, again, no fractions, but I still have work to do, but I recognize what I'm supposed to do. Oh, I can factor. Remember, you will never stop factoring for the rest of your life, at least for the rest of your math life. So I'm going to factor, and 2 times 1 is the only way I can make 2. I want minus 3 in the middle. 2 numbers that multiply to 2 and add to minus 3 is y minus 1, y minus 2. Here's my answers. Y is 1 or y is 2. Now let's check this out. Don't just circle these and walk away. Sorry, I had to slide the paper up. Can I get the paper and my checks in the same? Because remember, at the very beginning, you made a list of the forbidden numbers. And one of the forbidden numbers was 1. So I don't care that these came out of this equation. Like, this is math. I've got 2 answers. No, you only got 1 answer because this one is not legitimate. This is the only answer. You have to reject this answer because y cannot be 1. It would ruin the denominators. Now, I want to show you something visually, and then we're going to be approaching the break anyway. So why can't I use 1, apart from dividing by 0? And how do I know 2 works? Let me graph this right here in Desmos. Now, that's not our subject of our work today, but remember, I told you every equation is a graph. Every equation makes a graph. So no matter how short or how long the equation. So I'm just saying to myself, why don't we graph this equation? And let's find out why 1 is forbidden. And let's find out why 2 is an answer. So I'm going to go to Desmos and type this in. I can't have them both on my screen. Or I guess I could have them both on my screen at one time. Well, let's just open Desmos. You got the paper. You got both screens if you want them. I just had to carefully type this in. Now, I do have one problem right here is Desmos likes to think of graphs as made out of X's, not Y's. So I don't like this. It doesn't want me to type Y plus 2. See, this says try adding an X. Try adding an X, David. Okay, so first of all, I'll do it the way it wants it. X plus 2 divided by x squared minus x. And interesting to see what's going on. Not x to the x squared. Whoops. Okay, now I'm really screwing up. What is going on here? It's not. Okay, for some reason I confused it. Let's try it again. x plus 2 divided by. Interesting how x squared. Notice how Desmos, while I'm typing, even though I'm not finished, is trying to graph what I'm typing, minus x. So there's x plus 2 over x squared minus x. Now we're going to subtract 6 divided by x squared minus 1. Now, what was my equation? I wanted to know, remember, let's go back to the paper. Oh, I've never left the paper. Okay. Concentrate, Dave. I want to show you how Desmos tried to write the graph while I was typing. Do you see how it's trying to graph the thing I'm typing, even though I'm not done typing it? It's just typing what I have so far. Minus 6 divided by x squared. There's a lot of crazy stuff flashed on screen. Minus 1. Now remember what I was trying to do? I was trying to make this equal to 0. That's what I wanted. Tell me the x's where this is 0. That's the equation, except it had a y in it. Now let's look at this graph more carefully. This graph is like weird. I mean, maybe I can make it wider. It's got, looks like it's got a piece over here on the left shooting down. Then it's got a piece right here, kind of a thin sliver above that. And then it's got a piece over here shooting out to the right. But look at the scale, minus 10, 0, 10. What am I interested in? Excuse me. I'm interested in 2. I'm interested in 1. I'm interested in 0 and minus 1. Let's zoom in on just this area near 0 by saying the x-axis should be much smaller. Let's say minus 4 to 4. Okay, now I get an interesting graph. It's a little bit smaller than the previous one. And where is this graph equal to 0? Follow this graph with your finger. It's equal to 0 when it crosses the x-axis, right there. See, when x is 2, y is 0. Now, in our problem in the book, we use y for the variable. When y is 2, the output was 0. There's the moment where I get 2. And notice I cannot plug in 0 to this equation. I cannot plug in minus 1. Notice that at x equals 0 or at x equals minus 1, I have literally just emptiness. There's no red graph when x equals minus 1 or x equals 0. Now you said, but wait a minute, you said there's no graph when y equals 1, when x equals 1. I'm using x's right now instead of y's. What about when x equals 1? Well, again, let's slide our point in there and see what happens when I get to the part where x is 1. Notice what it said. When x was 1, in our equation where y is 1, this is undefined. So even Desmos admits that I cannot use 1 in this red graph. Now, when Desmos is drawing that red graph, it looks like it's using 1. If I zoom in on that, it looks like there's a red thing at 1. But as I go closer to 1, as I actually touch 1, the moment I touch 1, Desmos says, whoa, it can't go there. Undefined. So that's interesting. See the 3 problems? Cannot use minus 1. That's a black dashed wall. Cannot use 0. That's the other black dashed wall. But actually, there's a hidden problem here at 1. I cannot use 1. So I don't know if this is exciting to you or not, but I just wanted to show you every equation creates a graph. Every graph creates an equation. I don't see what would happen. If I change these to y's, you know what would happen is Desmos would graph it sideways, which I don't particularly want. But I just want to show you what would happen if I change those to y's. I don't think it would like it. You see, it's not even going to try to draw it. It says, try adding an x, David. How about if I tried to trick it by using a capital Y? You see what Desmos is saying to me? It says, do you want to make that a slider? No, I don't want to make it a slider. I want you to graph it. So that's funny. In order to get Desmos to graph this, I have to call the input variable x. Desmos is really, really useful and effective, but sometimes it's just picky and insists when you're making a graph that you write it in terms of x. I'll go backwards. Okay, if you insist, I'll write it in terms of x. To see later if we graph things like this. I don't know if we're going to graph things like this later or not. Maybe it would be another math course if you want to take another math course. But I just want to make a promise to you. Every equation is a graph. Every graph is an equation. Okay, that's worth the time spent looking at that picture. So what I'm going to do is, let's just say, got 12:59 right here. Let's take a break and come back at 1:05. And I might do a little bit of experiment writing on the whiteboard. So I'm going to mute my microphone while I just stretch my legs for a second. You guys can do similarly, and then we'll come back in a few minutes. Okay, we're back here and we're ready to apply this to some word problems. So your first reaction when you're doing these rational equations is, wow, these are crazy. Or like the graph I just showed you. What does that graph mean? What could I ever do with that graph? But it turns out that you can do some practical problems with rational equations. And this is section 6.6. It's called Applications of Rational Equations. I said to you, I wanted to do a little experiment where I step in front of the camera to the whiteboard. So I'm going to turn the recording on my whiteboard, but then you still have to have the problem. So I think there's issues with this. I just want to see if I can record one or two problems on the whiteboard, and I want to see how that messes with the bandwidth. So if we try this and it fails, then I won't do it again. But here, I want to show you two problems here at least. Let's look in the book, and I'll leave this problem 8 on the book window open, but I'm going to train my camera on the whiteboard. Okay, so let me read this problem to you, and then we'll write it on the board. Find a number that you would add to both the numerator and denominator of 8/11 so that the result would be 6/7. So one thing I don't like is rewriting the problem. So that's not always going to work. But like I said, this is an experiment. Find a number to add to the numerator and denominator of, what did it say? 8/11 so that the result would be 6/7. But there is one thing I like about working on the board and writing on the board, or just writing on scratch paper, is I don't want to always give you the impression that everything has to be perfect and like written exactly like a professional would write it. So I just like doing scratch work on a chalkboard or a whiteboard here. So find a number to add to the numerator and denominator of 8/11. So I'm thinking about adding a number to the numerator and denominator of 8/11 so that I would get 6/7. I also don't know what you think about the videos in the book. You can tell me whether you find them helpful or not, but I thought the videos were relatively nice, so maybe I should make a little more video like that. Okay, so is there a number I can add to 8/11 to make it 6/7? I mean, really, I'm being asked to solve this. And then check my answer. So let's do it as if we did the problems from the last section. I'm looking at a rational equation. When I read it, did you realize it was a rational equation? Yes, talks about numerator, denominator, talks about fractions. I want to make sure I don't divide by 0. So I'm going to make this note over here. Don't use -11. That would cause me to divide by 0. Other than that, I'm just going to multiply by the LCD. And the LCD here, 2 fractions, is just this one lacks a 7. This one lacks an 11 plus x. The least common denominator here is just 7 times 11 plus x. Or you could say x plus 11. Let's multiply both sides by 7 times 11 plus x. I would write another line usually on a piece of paper. So I'm being a little bit casual here, right? But I'll just write it on top of this problem. Here, I get to cancel the 11 plus x's, and I'll just have 7 times 8 plus x. That's all that's left after I cancel. Here, I cancel the 7, and I have left 6 times 11 plus x. That looks like a more ordinary equation. I just work it out, say 56 plus 7x is 66 plus 6x. If I subtract 6x from both sides, I'll only have 1x on the left. If I subtract 56 from both sides, I have 10. So they're saying that 10 is the magic number. So let's try it. I mean, 10 is certainly legal. I won't get in trouble if I use 10. But I'm just curious how that turns into 6 sevens. 8 plus 10, 11 plus 10. What do we got here? 18 over 21. And you can divide both top and bottom by 3. That's right. Think about factoring like that. That is 6 sevens. Okay, good deal. So the answer here is legitimately 10. I do one more thing, and I said this to you when I was grading your papers too. Remember, this is a word problem. They asked you the question in English. Even though it seems kind of silly here, answer the question in English. Let's do another word problem. Then it might make more sense why I have to answer in English. But let's just answer this in English. It doesn't mean I have to do anything fancy. Just say the number is 10. I think that's a better answer. Get in that habit. When someone asks you a question in English, you answer in English. Okay? I want to try another one, so I have to take the book away from there. And I'll put back the book in a second. But I was looking at problem 13. Let's look at problem 13. Yeah, let's try problem 13. I'm going to erase this. And let's do it on the board. And I won't write down the problem word for word because it's a little bit longer. But I will make the table that he has on the board. And I will tell you what it says in the problem. Now there's a downside of writing on the board. I got my back to you and I'm not looking at you all the time. Of course, when I'm writing on the paper, you don't see my face much either. Okay, let's check this out. 2 trains, train A, train B. I won't rewrite the whole problem, but let's write down the key facts. I got train A and train B. Train A has a speed 15 miles per hour greater than train B. I'll just write that down, 15 miles per hour faster. Well, what else to say? Train A travels 150 miles in the same time it takes train B to travel 120 miles. course, I also have to be careful not to write too small or too sloppy, right? So what else do we have to do here? He just pops out the question, what's the speed of the two trains? What's the speed of the two trains? So let me put this in front of the camera so you can read it if you want to read it. Let me make sure this is centered on the camera. In this sense, you can always center this in your video if you wanted to, but I'll go back to the whiteboard. So I realized when he asked the question, they didn't tell me about the train speeds. Think about that. They told me one was faster. They told me one travels 150 miles an hour, 150 miles, same time the train B travels 120. And so, that makes sense because train A is faster, but it didn't tell me the speeds of the trains. How am I supposed to work that out? Let's check this out. I'm just playing with the colors. Let's try, and the book suggests this, to make a table. And whenever you have a problem where, boat, plane, train, stuff like that going on, think about the key facts. The key facts is a speed, and people traditionally call that the rate of the train. The speed is the rate of travel. The other key word up here on the board is time. Time, same time. So rate times time is a very common idea. When you do rate times time, you get distance. That's the other thing on the board. Travels 150 miles. Travels 120 miles. So the way that I'm going to figure out how fast they're going, the speed, the rate, is by comparing the time and the distance they travel with this equation. Rate times time equals distance. If you drive 60 miles an hour for 3 hours, you drive 180 miles. It's 400 miles to Chicago from here, about. If I told you that I drove to Chicago in 4 hours, you'd be nervous. You'd be shocked. If it's 400 miles to Chicago and I can make it in 4 hours, no, I'm clearly exceeding the speed limit. In fact, I don't even think I could make it in 4 hours if I was allowed to exceed the speed limit because traffic and things like that, right? But if I said it's 400 miles to Chicago, it takes me about 5 hours. Then you'd be saying, okay, 400 miles, 5 hours, he's doing 80 miles an hour. It still seems a little bit fast. I mean, it's doable, maybe if there was no traffic. And then maybe if I cross over into Illinois, I slow down. Because always when you cross the border and the highway patrol's sitting there waiting to pick up the people that are zooming across the border, right? Okay, anyway, here's the situation. Let's fill in the table. That's how we're going to do it. What can we fill in? Because it doesn't look like we were given a lot. But let's think about it. I was given distance. I was told train A travels 150 miles. In the same time that train B travels 120. I was not given their rates. That's what I'm trying to find out. But I was told one key thing, that one was 15 miles an hour faster than the other. What are the speeds of the two trains? I don't know. The moment I say I don't know, that's a variable. let X, if you want to say X, be the speed of train A, or B, either one. But let's let X be the speed of train A, the rate of train A. I can actually fill in this box now, train B's speed. I don't know what it is, but I know it's 15 miles per hour what? Careful, slower than train A. In other words, if train A is doing 75, this one's doing 60. If train A is doing 200 bullet train, and train B is doing 185. So this is a very common problem like this, where you make a table. And very common thing when you make a table is you usually get one column for free. You get one column that you have to fill in with the variables. And then you get the other column by mixing these two. Think about what I said a second ago. I said Chicago is 400 miles away, and I can make it in 5 hours. Sorry, 5 hours. If Chicago's 400 miles away and I can make it in 5 hours, then you reasoned that I was doing 80 miles an hour. In fact, you were very upset when I said that I was going to drive 100 miles an hour. Because then I would get to Chicago in only how many hours? You fill in this number here, 100 miles an hour, 400 miles. It would only take me 4 hours. But how did you fill in that number? You literally divided that by 100. How should I fill in this box here and here? I could do the same thing. I could divide that box by that box. Even though I don't know this, I could divide 150 by X. Because if I do know what X is, that will be the time. What if X was 3? I don't know what 3 means, but let's just say X was 3. And this would be 3 times what is 150? 3 times 50 is 150. What if X is 50? 50 times what is 150? 150 divided by 50 gives me 3. 50 times 3 is 150. You see, I'm allowed to fill in this box using these two. I'm allowed to fill in this box by saying 120 over X minus 15. And now I have an equation. Same time. How does train A do 150 miles? In the same time that train B does 120. I can set these two times equal to each other. And guess what? I've got a rational equation. So let's use this idea of same time. This train does 150 miles in the same time this train does 120. So I can make these two equal to each other. It's not a big rational equation, but it's a rational equation. Now remember, let's solve and check it. Solve, check. I already know what I'm going to check. I cannot use 0 for X. I cannot use 2 for X. So remember, that's my recommendation. Write that down right away. Then you won't forget it. What about my LCD? Least common denominator? Well, I've got two denominators. I just multiply them together. X times X minus 2, X times X minus 2. That's what's missing. Left side is missing X minus 2. The right side is missing an X factor. So let's multiply both sides by X times X minus 2. What color have I not used? Okay, let's try green. Although I admit it's a little crowded right here. Okay, let's go down. On this side, I cancel out the x's, and I have 150 times x minus 2. On this side, right side, I cancel out the x minus 2's, and I have 120 times x. That looks not so bad. 150 times x minus 300 is 120 times x. I could put the 300 on the right. I could put the 120x over here on the left. Subtract 120x. I get 30 x's. Add 300 to both sides. I get 300. And I can find out what x is very quickly. Say, divide by 30, or I could just see, oh, x must be 10. Divide by 30 on both sides, x must be 10.
I'm sorry, but how did you get x minus 2 for the...
Good, go ahead.
Because if 120 over x minus 15 were saying them equal, wouldn't it be 150 over x equals 120 over x minus 15?
Okay, so someone's in serious trouble here, and it must be me.
I'm sorry if I didn't understand something. I'm just confused.
No, I did something stupid, didn't I? Well, don't ever say stupid, just you did a mistake. Okay, let's fix it. What did I do? I mean, I wrote x minus 15 there. Of course it's x minus 15. So let's just fix it. When that happens, don't panic. Just one at a time, go through and fix. That better be a 15. Thank you. Very good. See, I was so happy that the answer was nice, I didn't even pay attention to what I was doing. That's a 15. Now, that means I have to change what I'm doing here. I don't use 0 and I don't use 15. I'm just slowly tracking everywhere I screwed up, and then let's fix it. That means my least common denominator is x times x minus 15. Thank you, very good. That means I'm going to multiply by x times x minus 15. Both sides. Although this is even more crowded now. Okay, let's just deal with it. Now let's fix the next one. Over here, thankfully, that didn't cause much damage. Just 120 times x still. So that side is okay. Over here, I cancel out the x and I have 150 times x minus 15, not 2. I don't know why I picked 2. Okay, but we're on our way. We're slowly fixing everything. This is fine. 150 times x is fine. What's 150 times 15? I'm going to pull out my calculator for that. 225, 0, 2,250. Good. That's better. Now you might say, no, that's worse. That's a terrible number. I rather have the 300 back. Now, on the other hand, though, are you going to look me in the eye and say that train's going 10 miles an hour? Well, maybe. But then the other train's going minus 5 miles an hour. And we knew we were in trouble. Okay, let's try to fix this. So the 30x is good. Subtract 120. Let's add 2250 to both sides. Now the number is not as sweet as it was a second ago, but what is x right here? If you divide by 30. Actually, it goes in evenly, does it?
Yeah, it's 75.
Good. Okay, now that doesn't mean we're right, but at least I got a nice number. Let's see if it works. I'll show you how we see if that works. Do you understand? If x is 75, then I could just put it right in here. 75, what would be 150 divided by 75? 2. 75 times 2 is 150. Check. Now let's put 75 in here. This will make this 60. What is 120 divided by 60? 2. That's what we wanted, same time. And 60 times 2 is 120. Check. Okay, now I feel much better. Now you've done everything right. Don't get too proud of yourself. Answer the question. You're so proud that you did everything right, you just walk away. No, it's time to answer the question. You don't have to write a novel. You just have to answer the question. What are the speeds of the two trains? I'll just say it plainly. Train A goes 75 miles per hour. Train B goes 60 miles per hour. We checked it. We know it works. We're happy. What else do I want to say about this? This seems very slow for a train. Now, I've been on fast trains and I've been on slow trains, but typical from here to there across the country in Amtrak, you might surprise people that they don't go too fast. I think we need to upgrade some train tracks, right? Amtrak passenger train just running cross country, it's probably averaging 80 miles an hour. You say, well, that's worthless. I could just drive. No, the train is driving while you're sleeping too. So to actually go cross country in an Amtrak train, maybe take 2.5 days. But that's 2.5 days instead of you driving cross country in 4 days or 5 days because you got to take a break. If you're careful, you ought to take a break. So 75 miles per hour sounds terrible as far as speed goes because, bullet train in Japan or electric trains, TSVs in Germany, they're doing 180 miles an hour, 160 miles an hour, even over 200 miles an hour. Those are commuter trains. That's the kind of train I want to ride, right? But we're going to have to upgrade some tracks seriously if we want to do that. Okay. I think I'm going to end that experiment because I just want to see how it came out myself. Let's do some more problems. We got more time to do problems, of course, but I don't want to do everything on the board. I just want to see how that worked out video recording wise. And of course, you can tell me whether you think it's better or worse from your perspective. Sometimes it's handy to see someone doing something besides just, here's the magic hand. Magic hand is doing math problems. Sometimes it's better to see a person. In fact, I think that's part of the thing I'm missing in this whole mess is you're at home and you never see any people. Right? Okay. And of course, you do see people. You just don't see all the people you used to see. Let me show you another problem. So I'm going to page through the book. I'm going to page through the book, but I'm going to do something particular here. And by the way, in that problem that we just did there, X was 75. It wasn't 0. It wasn't 15. So I kept my eye on that, right? But I checked the 75 in another way. Notice I also added the units to the answer, said 75 miles per hour, not just 75. But in the book, these are the kind of problem we got. Number problems, that's the first one we did. We did number 8. Rate problems. Or sometimes people call these rate times time equals distance problems, because that's how you do them. You set up a table where you have distance, rate, and time. In fact, he was trying to train you to make a table. Train you, no pun intended. But there's another set of problems in here that's really useful. And these are called work problems. I want to do one of these. A work problem. So in this rate times time equals distance problem, I actually used a rational equation. When would you ever use a rational equation? Well, we just did. But work problems are another example where you can use a rational equation to do something that sounds hard. These problems sound kind of weird, or like, how am I going to do that? But work problems, this is a great way to use rational equations. Okay, so let's check this out. And I don't want to write the problem on the paper, but maybe one I will. Because writing the problem on the paper, you have it in your book, but you want to also see the problem in your screen too, right? So let me abbreviate. Doug paints room in 4 hours. Elaine could paint same room in 6 hours. Together, how long would it take them? I mean, apart from the fact that this is a math class, you wouldn't even necessarily think that's a math problem, except it's got numbers in it. Okay, but what does this have to do with rational equations? Now, first of all, Doug paints the room in 4 hours, Elaine paints in 6 hours. That's because Doug's just tossing paint on the walls. Elaine is tucking the paint in the corners very nicely, right? So the goal when you're painting your room is not to paint it as fast as you can. Well, you want to paint it quickly, sure, but the goal is to paint it nicely. So Elaine is taking her time and painting it nicely. But let's think about this. When you start thinking about this, the first reaction is like, well, what am I supposed to do with this? Where's the equation? You know that you're not supposed to add 4 hours and 6 hours. Doug paints the room in 4 hours. Elaine paints it in 6 hours. Together, it will take them 10 hours to paint the room. No, that's ridiculous. Because if they're helping each other at all, they should be faster. Maybe when they paint the room together, they don't help each other. That's okay. But let's just pretend they were helping each other. It can't be that you add the numbers. Okay, that's the first rookie mistake. If you just read this problem to someone on the street without even thinking, they would say 4 plus 6 is 10. Okay, let's try another one. 4 plus 6 is 10. No, that doesn't make sense. Oh, I know. Doug paints the room in 4 hours. Elaine paints in 6 hours. Let's take the average. Maybe together they take 5 hours. No, that doesn't make sense either, because again, if Doug can paint in 4 hours and Elaine's helping, it won't take longer to paint the room than Doug could paint it by himself. Okay, see, so something is not right here. You're not sure how to make the equation. I'll show you how to make the equation, and it's a great way to use rational equations. So let's actually think about it this way. Doug, Elaine, and working together. And he illustrates this in the book too. I like the way he presents this in the book. So I'm going to say it the same way he does say it. And he does this in an example like example 4 and example 5. He does examples like this. Okay, let's try it out. So we know how long it takes them. Sorry. Well, we know how long it takes Doug, and we know how long it takes Elaine. How long does it take them together? And the first words that come out of your mouth are, I don't know. That's okay. I don't know is the variable. Usually when you say, I don't know, that you can make that the variable. But I can't just say X is 6 plus 4. That didn't make sense. But how about this? How about taking how long and turning it on its head? Instead of how long does it take them to paint the room? How about how much do they do in 1 hour? Let's think like that. I'm writing a little too much, I'm writing a little sloppily, but let's just think out loud. If it takes Doug 4 hours to paint the room, then in 1 hour, he's going to do what? 1/4 of the room. That makes sense. If he could paint the room in 2 hours, then in 1 hour, he'd do half the room, and the other hour, he'd do the other half. Same thing for Elaine. If it takes her 6 hours to paint the room, then in 1 hour, she would do 1/6 of the room. Now you can say the same thing about together. And you say, but you didn't tell me how many hours they did it together. Doesn't matter. If they use X hours to paint the room, then this reciprocal thing makes sense. They have painted 1/X of the room in X hour, in 1 hour. Now I got something I can add. He paints 1/4 of the room in 1 hour. Now I can say to myself, in 1 hour, I know this. Doug covers 1/4 of the room, and Elaine, covers 1/6 of the room. And I even know that when I add them together, I get 1/X. There's my equation. There's my rational equation. Now, this is the first example in that work problem section, so it's not a long one. But I still have work to do. But I have an equation. I have a rational equation. So work problems, these are traditionally called work problems. When you say, this person works this fast and this person works that fast, or later. The faucet fills the tub in 20 minutes and this other faucet fills the tub in 10 minutes. You know, two things working together. Or even the faucet fills the tub in 20 minutes and the drain can drain the tub in 10 minutes. Well, that's good because the drain is draining faster than the faucet's filling. You'd be upset if it said faucet fills the tub in 10 minutes, but the drain empties the tub in 20 minutes. You'd be upset. Why? Because, well, you're going to overflow the tub. Okay, let's go back to solve the problem. Here's my problem. Let's solve and check. I'll bring it up here. I don't need the words anymore. Before I start, I know that I will be concerned if I get 0. If x is 0, I'm in trouble, so let's not use 0. How about LCD? LCD, 3 denominators. I don't need to do anything but multiply them, really. I need to put a 6 and an x here, a 4 and an x here, and I need to put a 6 and a 4 over here. I need the LCD of 24x. Now, I multiply both sides by 24x. And let's see what happens. Why is multiplying by the LCD so cool? Because it immediately eliminates all the fractions. Sorry, I need an x right there. My fault. Okay, let's multiply. 24x times 1 over x is just straight 24. X is canceled. How about 24x times 1/4? Then you get a 4's to cancel, and you're left with 6x. How about 24x times 1/6? Get 6's to cancel, and you're left with 4x with a plus sign in between. If you need to put parentheses around this, like it was 4x plus something else, and you were subtracting, then you need parentheses, right? But right now, I just have 6x plus 4x straight up, which is 10x. What do you know about this number, 24 over 10? So, oh, I don't like it because it's a fraction. Well, that's true, but let's just live with it. 24 over 10, we could simplify it, right? And say 5 by 2, 12 over 5. Or you could say 2 2/5 hours. Sure, you could. But because that's the number of hours it's going to take them together. I feel good about that because notice how they got faster. That's what I hoped, they would get faster. 2 2/5 hours. I guess I don't mind if you say 12/5 hours or 2 2/5 hours, but I just want to think like a human. A fifth of an hour is what, 12 minutes? Each hour has 60 minutes, right? So 2/5 of an hour, 2 times 12 is 24 minutes. So it's 2 hours and 24 minutes. Now let's remember, let's say it in English. What was the question? How long would it take them together? And I'll just say together. It takes them 2 hours and 24 minutes to paint the room. Don't have to write a novel. You just have to write a complete sentence. Someday I'll have to teach math class plus English class together. And they can correct my English. And I can correct their math. But I think it would be fun to, write a whole story about math problem. And then I could write a novel to do the math problem answer. Okay, I'm done. This is it. Now you could check to see if it works by plugging 12 over 5 into here. Because when you do 1 divided by 12/5, that would become 5/12. We're taking the reciprocal of 12/5. That's 5/12. And if you got common denominators here, 12s, you'd be talking about 3 12s plus 2 12s, which is 5 12s. Okay, so it actually physically works. But I was feeling very good the moment I saw it was not 0. because I figured, okay, I'm not going to divide by 0 because x is not 0. I'm feeling good about the answer as long as I did everything else right. Okay, good. So this is, well, let me leave this up here for a second because I think we'll just cut it right here today. This is a famous problem. It's called a work problem. So think about a work problem like this. Make a table like you did the train problem. First, list how long it takes them to do the whole job. This was the whole job. Then find out how much it takes them to do in 1 hour. What part of the job do they do in 1 hour? Or 1 day, or 1 minute, or 1 year, whatever is the time units you're using. This was in 1 hour. Okay. What else are you going to do right here? Okay, so you dig into these problems. Remember, this is the problems for your homework that's coming up this next week. These problems are due next week. You have on the website a homework problem ready for you to do. And this is due on, when is the 4th? I'm trying to think ahead. Is the 4th next Wednesday? I want to make sure I got my dates right. It's November. It's November already. Yes. So November 4th is a Wednesday. We're doing that right. And where did my screen go? So just sharing the screen with you. And the screen is acting up.
Hey, Professor, I have a question.
Go ahead.
Do we have a final exam?
Good, good. The answer is yes and no. You have a last exam. It's exam number 2. But remember, it's just going to cover the second part of the course. I was not trying to go intense on the exams. Now, however, that's not a freebie, because if you had to choose between the first part of the course and the second part of the course, which one's easier? First part of the course. So the second exam is in the last week. It's on our schedule on our website, but the second exam only covers the second half of the course. Okay, anyway, you were doing irrational equations, adding, subtracting here. This is, it's a little bit like rational equation. Okay, you just do this problem. This is the problem for next Wednesday. Factor, cancel, simplify, multiply, subtract. You attack this, and then we'll see you next week. You guys have a great day. Go outside and get some fresh air. Talk to people. I'll see you later.